Welcome back, everybody. I'm very happy to introduce my academic sister, Sarah Mason, and she's going to talk about lifting the dual immaculate functions.
Okay, I'd like to start by thanking the organizers for getting this conference online, and I also want to say a special thanks to them for getting everything posted to the website so quickly. I actually teach synchronously during most of the talks, and it's been really nice to be able to go on later and watch some of the talks that I missed. So thank you. And all of this is joint work with Dominique Searles at the University of Otago. This project is motivated by some recent work of Asaf and Searles. They've developed a research program of lifting bases for quasi-symmetric functions up to the polynomial ring. One nice example of this is their fundamental slide polynomials, which are functions that actually have positive structure constants. And in fact, Schubert polynomials expand into positive sums of fundamental slides. They also have produced some other really nice results, lifting a number of other QSIM bases as well. So our initial goal began with lifting the dual immaculate quasi-symmetric functions up to the polynomial ring. And we'll start by giving a background on dual immaculates and some other key players in this work. But then we'll get to an obstruction that turns out to have deeper and more meaningful consequences than we initially realized. And this is a notion of something that we'll call Young and reverse families. Once we've explored this a little bit, we'll return to our goal of lifting the dual immaculates. And then at the end, we'll say a few words about another family, a young version of the key polynomials. Okay. So our main objects of study for this talk are symmetric polynomials, quasi-symmetric polynomials, and polynomials. And we will restrict ourselves to n variables for reasons that will shortly become apparent. But I've also color-coded this so that it becomes clear which objects we're dealing with and what space they live in. So the polynomial ring is our main goal for this talk, and this is just polynomials in n variables. Bases for this ring are indexed by weak compositions, which are sequences of non-negative integers, so meaning we have some zeros. And so, for example, the monomial basis, which is literally monomials, and you can think of those as being, if you take a weak composition, you raise your first variable to the first part of your composition, the second variable to your second part, and so on. So here's our example for 204. Then inside the polynomial ring sits quasi-symmetric polynomials. And these are polynomials that are shift invariant in the sense that if you write down all the exponents of one of your monomials, then including the zero exponent. So if one of the variables doesn't appear, you give it an exponent 0, then all of the monomials that you can obtain by shifting around your zeros must also appear in the polynomial. So for example, here we have, ooh, something's disappeared from my slide. There's supposed to be an M there. Hopefully that's not a problem throughout. But in any case, that quasi-symmetric polynomial has exponent, like if you look at the first monomial, it's 240, and so then you also need to be able to shift the zeros around and get things like 204 and 024. You don't have to switch the order of the 4 and the 2, but if you did and you got 420, then you would also need 402 and 042. And then finally, inside QSIM sits the ring of symmetric polynomials, which we'll use red to denote these. And these are all the polynomials that are invariant under the action of the symmetric group that permutes the indices. And so here we've written down the monomial symmetric function. So we use red for sim, purple for QSIM, and blue for polynomials. Okay, good. So now bases for the polynomial ring, as we said, are indexed by weak compositions, and again, I'm using blue for these. So we have some of our classical bases, monomials, de Majeur, Adams, key polynomials, and then as we mentioned, there's some recently introduced bases by Asaf and Searles, such as the monomial slide polynomials, fundamental slide polynomials. and so on. In QSIM, which we're going to use purple, and these are indexed by compositions, which are sequences of positive integers. We have monomials, there's the fundamentals, quasi-symmetric Schurs, and dual immaculates are all bases for QSIM that are closely related to Schur functions and could, for various reasons, be considered as quasi-symmetric analogs of Schur functions. And then symmetric functions are indexed by partitions, which are weakly decreasing sequences of positive integers. And so we have lots of well-known bases for these, including especially the Schur functions. And many of these bases have combinatorial descriptions in terms of tableau-like diagrams, and those are going to play a role in what we're going to do. Okay, so our main question that started out this project was, if you look down in quasi-symmetric land, you have the dual immaculate quasi-symmetric functions that were introduced by Berg, Bergeron, Saliola, Serrano, and Zabracki, and those expand into a positive sum of young quasi-symmetric Schurs, which expand into a positive sum of Gessel's fundamental quasi-symmetric functions. So up in polynomial world, we wanted to lift the dual immaculates in such a way that they expanded into a positive sum of something called the quasi-key polynomials, which are a lifting of quasi-symmetric Schurs. And the quasi-key polynomials expand into a positive sum of fundamental slide polynomials. Now, the problem is, when we tried to do this the naive way of just lifting the dual immaculates directly, they actually didn't expand into a positive sum of the quasi-key polynomials. And the reason behind that was something that we thought was just a phenomenon in the quasi-symmetric Schur picture, but turns out to be a much broader phenomenon that has some pretty interesting meaning. So the quasi-symmetric Schur functions, and I'll define all of this in a moment, I'm just kind of giving an overview right now, split into two families, one that's called the young quasi-symmetric Schurs, and the other, the originally defined quasi-symmetric Schurs. Both of those expand positively into the fundamentals. And so we sort of thought that this splitting into two families was something that was distinct to the quasi-symmetric Schur world, especially because it didn't seem to have, we didn't see it in the fundamentals. And so it turns out that the lifts up to the polynomial ring were connected to the, what we'll call the reverse setting of everything. And so in fact, instead of needing to just lift our dual immaculates, we needed a notion of a reverse dual immaculate. And then we needed to lift all the young things, in fact, including the fundamental slides. So even though the fundamentals don't split into two families in QSIM, they do in the polynomial ring. And so that is the, these are the pictures that we wanted to fill in. Those are the correct pictures to look at. Okay, so now for some definitions. So sort of to motivate where the dual immaculates come from, we need to go to non-commutative symmetric functions. And there's a really beautiful paper by Gelfand, Krob, Lescu, Leclerc, Raytok, and Thibon that describes this, just very, very nicely. There's lots of other important references, but this was the one I wanted to point you to. So this space is generated by objects called the capital H's, and they're a multiplicative basis in the sense that when you take a composition, and these are compositions without zero, so strong compositions, H sub alpha is equal to H alpha 1 times H alpha 2, and so on. And as a Hopf algebra, the NSIM is dual to quasi-symmetric functions under the inner product that under which the monomial quasi-symmetric functions are dual to the H's. So the Schur functions in SIM can be, one of the ways to generate the Schur function is to use something called creation operators. And so what Bergeron, Saliola, Serrano, Zabracki did is they generalized these creation operators into NSIM and then applied the same process that you would use in SIM to generate the Schurs, and they got something they called the immaculate basis for NSIM. And this basis actually projects to the Schurs under under the forgetful map, which is the map that says just forget that your variables don't commute. And the object that we are going to focus on in this talk is the quasi-symmetric function that is dual to the immaculate basis under this inner product. So let's go ahead and get a combinatorial description of this. So a semi-standard immaculate tableau of shape alpha is a filling, and we'll use French notation, which is the horizontal flip of what they used in their paper. But so the row entries weakly increase from left to right, and entries in the leftmost column strictly increase from bottom to top. So there's no other column entry condition. And then the dual immaculate quasi-symmetric function can be defined as the generating function for the weights of these semi-standard immaculate tableau. And so here's an example. And some of the nice properties of these dual immaculate quasi-symmetric functions, they have a signed multiplicity-free Peary rule. There you can expand Schur functions into not positive sums, but you can expand Schur functions into signed sums of dual immaculates. They have a representation theoretic meaning, and they also expand into positive sums of Young quasi-symmetric Schur functions. And so if you recall, that relationship was the one that we wanted to kind of focus on building in the polynomial ring. Okay, so in order to understand what these Young quasi-symmetric Schur functions are, we need to back up into where they came from as well. And so McDonald polynomials, which were introduced by McDonald in 1988, satisfy a triangularity requirement with respect to the monomial symmetric functions, and also they're orthonormal with respect to a certain QT inner product. When introduced, McDonald conjectured that their coefficients, when expanded in terms of the Schurs, were positive. Mark Heyman proved this using the geometry of Hilbert schemes. It's still an open problem to find a combinatorial formula for these coefficients. There also, you can get all sorts of different symmetric function bases by specializing the Q and the T. Oh, and I should say these are symmetric in the X variable, and then with just an additional Q and T parameter. And then Raman, you have to generalize these to all Lie types using like Littleman path ACOW walk style methods. Okay, so in 2008, Hagelin, Heyman, and Lohr introduced a combinatorial formula for McDonald polynomials, and I'm not going to go through the definition of it, but what you should notice is that the inv is in some sense telling you some things about columns and some orders on the entries. And then there's also non-symmetric McDonald polynomials, which have been studied by many people, including Cherednik, McDonald, Optum, and Heckman. And these also satisfy a triangularity and orthogonality requirement. You can realize them as eigenfunctions, and they symmetrize to McDonald polynomials in the following way. So the non-symmetric McDonalds are still live in the polynomial world with an additional QT parameter. And essentially, when you take all the weak compositions that when you rearrange their parts into decreasing order, you get a certain partition, and then you have additional coefficients with Q's and T's, then you get the symmetric McDonald polynomial. When you set Q and T equal to infinity, on the left-hand side you get the Schur function, and on the right-hand side you get something that we'll call de Majeur atoms. And so remember, these de Majeur atoms are going to be indexed by weak compositions. And so what we do to define the quasi-symmetric Schur functions is we sum over all of the de Majeur atoms that collapse to a given composition. And what we mean by that is when you remove the zeros. So for example, the quasi-symmetric Schur function indexed by 1, 2 is given by the atom 1, 2, 0, 1, 0, 2, and 0, 1, 2. Okay, so let's also get down a tableau description of these. So Semi-standard reverse composition tableau of shape alpha satisfies the rules that the row entries have to increase from left to right weekly. The leftmost column entries have to strictly increase from bottom to top. And then there's a triple rule which really governs the orders of the column entries. And so the quasi-symmetric Schur functions are the generating functions for these particular, the weights of these tableaux. And some of their important properties include the fact that the Schur functions decompose into a positive sum by simply rearranging the parts of the given Schur function. So S322 decomposes into QS322, 232, and 2. Oh, that's supposed to be 223 there. And so one result but based on this is that, in fact, if a symmetric function is quasi-symmetric Schur positive, then it will actually just be Schur positive as well. They also decompose into a positive sum of fundamentals. There's a nice variation on the Littlewood-Richardson rule that allows you to multiply an arbitrary quasi-symmetric Schur times an arbitrary Schur and expand into the quasi-symmetric Schurs with positive coefficients. They also have a representation theoretic interpretation. They are specializations of recently introduced quasi-symmetric analogs of McDonald polynomials, but they don't play nicely with the dual maculates. So trying to write the dual maculates in terms of quasi-symmetric Schurs doesn't yield anything nice. So here's where the flip and reverse picture, which is this Young and reverse families, comes up. So the Young quasi-symmetric Schur functions can also be defined as generating functions of certain tableau. And essentially what we're doing is just basically a flip and reversal of a variable. So it's not a, yes, Darius asked if YS would be the same thing as YQS. Yeah, this notation hasn't necessarily standardized. Okay, so, but these do play nicely with the Young the Young quasi-symmetric Schurs do play nicely with the dual maculates. So there's a nice positive expansion of the dual maculates into Young quasi-symmetric Schurs. And that's the formula that we wanted to lift to the polynomial ring. Okay, so let's just say a few words about this flipping and reversing. So if you think about what happens when you, oh, and I guess, yeah, I didn't say much about this over here, but let me back up. So for the Young quasi-symmetric Schurs, to get between the Young quasi-symmetric Schurs and the quasi-symmetric Schurs, you replace x1 with xn, x2 with xn minus 1, and so on, and then you reverse your composition, meaning you just write the last entry first, and so on. Okay, so when you flip your variables like that in a symmetric function, of course it doesn't change anything because that's what it means to be symmetric. But as soon as you get into QSym or the polynomial ring, things do change when you do this. Sammy has a question about infinitely many variables. There's the limiting stuff that you can do in that situation, but this is the reason why we are sticking to finite variables for now. Okay, so when we kind of looked at which functions play nicely with the Young quasi-symmetric Schurs and which objects play nicely with the quasi-symmetric Schurs, one thing we noticed is that when you look at the tableau models, the things that play nicely with quasi-symmetric Schurs tend to have tableau models where their row entries decrease, whereas the Young quasi-symmetric Schurs and the dual maculates have tableau models where the row entries increase. So they sort of seem to be splitting into increasing and decreasing families, and that's sort of the notion for reverse to describe some of the lifts of these decreasing families. We use Young for the increasing families because that's what the Young quasi-symmetric Schurs were called. And they were really introduced, I think, partly so that they played a little bit nicer with the typical semi-standard Young tableau descriptions of the Schur functions. Okay, so now that we've talked a little bit about this flip and reverse, we want to go ahead and do this for the dual immaculates. So the actual act of flipping and reversing is straightforward, right? We say, let's define the reverse dual immaculate quasi-symmetric function by flipping the variables and reversing the indexing composition. And of course, when we do that, then we can write down fillings that that the reverse dual immaculate quasi-symmetric function is the generating function for. And now, because of this flip and reversal, we get that the reverse dual immaculate quasi-symmetric functions expand positively into the quasi-symmetric Schur basis, which is really what we need when we want to lift up to the polynomial world, where we have a little bit more work to actually do. So now we have what we need in the quasi-symmetric world, and we're going to lift up to the polynomial world. And Zachary Hamaker asked about reversing playing with the inner product in non-commutative symmetric functions. That is something that we're interested in looking at and haven't spent much time on at this point. Okay, so now we're able to lift to polynomials, and so we need a few definitions before we can get to what we're doing in the polynomial ring. So first of all, I guess we've already mentioned this, but if we have a weak composition and we remove all the zeros, that's called the flat of the composition. And then dominance order, we say B is greater than or equal to A in dominance order if the partial sum of the first K entries of B is greater than or equal to the partial sum of the first K entries of A for all K. And then finally, we say that B refines A if you can get A from B by summing collections of adjacent parts of B. So you take pieces of B and add them together, consecutive pieces of B, and add them together until you get the coarser thing A. So refining for us means smaller pieces. And so Asif and Cyril's use this to define the fundamental slide polynomials. And the reason they're called slide polynomials is you can kind of think about it as sliding the exponents over. So here we start with this x1 squared, x3 cubed, and the x1 squared, well, that squared can't really move any farther to the left because there's no variable over there, but the cubed on the 3 can start marching to the left until it hits an obstruction of a variable that was already there. So that's the definition for the fundamental slide polynomials. And again, they have positive structure constants. The Schubert polynomials expand positively into them. And if you take the limit if you start, padding with zeros in front of your composition, then you get back Gestel's fundamentals. And then there's also a nice relationship to something called quasi-key polynomials, which is a lift of the quasi-symmetric Schur functions. And so again, the quasi-key polynomials can be described by tableau. And these tableau models are really nice because they allow us to do to understand what's happening with flipping and reversing, sort of diagrammatically. And so basically the row entries weakly decrease, column entries are all distinct. All triples are inversion triples. And then there's also this additional flag condition that says that the entries in row I must be less than or equal to I. And so then we take the generating function of those, and these also limit to the quasi-symmetric Schurs when you pad the front with zeros. Okay, I see some chats. I'm gonna maybe I'll try to respond to that later. Okay, so now we're in a position that we can go ahead and lift the dual immaculate slide polynomials. And so here again, if we think about the tableau definition, it's going to look a lot like the tableau definition for the dual immaculates, except we have this additional flag condition that says that the entries in the ith row from the bottom are greater than or equal to I. And we can show that in fact this lifting of the dual immaculates will be quasi-symmetric if the indexing composition A doesn't have any zeros to the left of its first of a non-zero entry. So in other words, once you get a non-zero entry, you So you just can't have zeros first. It has to be kind of like non-zero. Once you get a zero, sorry, you can't have any non-zeros after that. But that's the only way you're going to get to QSIM from these. So there's not a limit. There's not like a stable limit like we saw for the quasi keys on the fundamental slides. You can't actually take a limit and get to your dual immaculates. And so that's one of the things that's sort of different in this Young picture, because the dual immaculates really fit in the Young picture. So that's something that's different here. But so we did want to go ahead and write these in terms of fundamentals. We just needed the Young fundamental slides. And so we take the fundamental slides and we just reverse the weak composition and flip the variables. And then in order to figure out, so that gave us the, the target object. And then in order to show that, in fact, the dual immaculate slides did decompose into a positive sum of Young fundamental slides, we adapted a notion of a weak descent composition from some work of Asaf's, where I think she was using it in relation to expanding maybe Schubert's and Key's in terms of fundamental slides. So we're able to modify that and prove this expansion. And then we also finally get to our main goal of the project, remember, was once we lift to polynomials, is we want to make sure that the same relationships hold. And so first we needed the Young quasi keys. And so again, flip and reverse. And I resisted the urge to include any Missy Elliott background music, quotes, for those of you who know her flip and reverse song. Let's see. So yeah, so this was generalizing the result in QSIM that says the dual immaculates expand into the quasi-symmetric Schurs. So we needed to come up with an analog of the dual immaculate recording tableau. We needed to do insertion, and remember, we now have this additional flag condition that we had to deal with, and then we needed to invert the insertion. But that's sort of the basic components of the proof here. We're modifying what happened in QSIM, but you can't actually get the QSIM result. You can't travel back and forth between them because you sorry, I'm laughing at the chat. The chat is I need to turn it off because it's distracting me. I'm gonna hide it for now. And if there's something that I need to address, just let me know. Okay, so you can't actually go back and forth between them. You can't go from QSIM ratcheting up to polynomial, and things are generally just a little bit harder in polynomials than in QSIM. But you also can't, for this particular result, we can't go down to the QSIM world because we can't take those stable limits here. However, if we move to our reverse dual immaculate slide polynomials, which now again we can flip and reverse, and we get this formula, the expansion into fundamental slides, we can now get for free from our dual immaculate slides into Young fundamental slides by taking flip and reverse of both sides. And the reverse dual immaculate slides do have stable limits and nicely limit to the reverse dual immaculates that we just defined. And so we can obtain our, like the expansion of the dual immaculates into Gessel's fundamentals by first taking a stable limit of the reverse formula and then applying flip and reverse. Okay, so yeah, so just to summarize, we've now filled in our pictures that we wanted. And I also want to just spend the last few minutes talking about one other Young family, because obviously a natural next step with this project is to go ahead and look at what happens with reverse and Young families across the board, for example, with non-symmetric McDonald polynomials, with Schubert polynomials. And Young key polynomials is a Young variation on key polynomials. And so just to say a few words about that and something interesting that came up with that. So the key polynomials, which are really type A de Moivre characters, if you're familiar with that, and a really amazing paper that's already been referenced in other talks at this conference is the Key Polynomials and the Flagged Littlewood-Richardson Rule by Reiner and Shimizuno. So if you have a weak, but I'll define these. So there's lots of different ways to define a key polynomial, but since we've already seen the de Measure atoms in this talk, I'll go ahead and define it through de Measure atoms. If you take a weak composition and then you sum over all weak compositions that are smaller than your initial weak composition in Bruhat order, you sum over the de Measure atoms, you get your key polynomial. So for those of you who like crystal graphs, here's a quick picture of that. And then the keys, which is, there's different ways to define them in terms of keys, but a key is a semi-standard Young tableau whose column entries are subsets of one another. So like your second column entries, the set of entries in the second column are a subset of the set of entries in the first column, and so on. And each weak composition corresponds to a key by taking, like you take your first part of your composition, you write down that many ones starting in the leftmost column. And then your second part, you write down that many twos. Your third part, you write down that many threes, so that you're forcing the columns to be subsets of one another. And so I'm not going to define right and left keys. It's a complicated definition that involves Knuth equivalence and Schoenstatt insertions and things like that. But I really like the method of computing them that Matthew Willis discovered in this paper, A Direct Way to Find the Right Key of a Semi-Standard Young Tableau. And so the basic idea, we have right keys that are, you start with a semi-standard Young tableau and you move, you start on the right-hand side and you create a key moving from the right. And the left key, in some sense, you start on the left-hand side. And so in this case, we have like 1, 2, 3, 5. So we know that's the first column, and then the remaining columns are subsets of that. And in 1990, Lescaut and Schutz and Berger showed that, in fact, the key polynomials are generating functions for all semi-standard Young tableau whose right key is less than or equal to the key of its indexing composition. And so then when we defined the Young key polynomials, it turns out that these Young key polynomials, so with this flip and reverse, happen to also be the generating functions for the left keys. So the semi-standard Young tableau whose left key is greater than or equal to the key of the indexing composition. So the flip and reverse is also matching up with moving between right and left keys. And finally, one last thing, there is like some representation theoretic meaning to this. So Reiner and Shimizuno proved that the key polynomial is a trace of the action of a diagonal matrix, a GLN, on a certain key module, and we could modify this result appropriately to construct something called a Young key module. And then our Young key polynomial is in fact a trace of the same matrix acting on this variation of the key module. And I guess with that, I'll just mention a few future directions. So you can, one goal that we have is to just go ahead and look at what happens when we do this flipping and reversing for other families of polynomials and see if we find something nice, such as this this left key generating function. We also want to look at non-symmetric McDonald polynomials and Schubert polynomials in particular. And then, as someone mentioned, well, I guess they mentioned the inner product, but we'd really like to understand the creation operators in the dual immaculates, because of course, since we have a reverse dual immaculate in QSIM, it has a dual in NSIM. And we'd like to understand, can you write down creation operators to construct it, and kind of what does that mean? And so those are some directions that we'll go moving forward.
Thank you so much. So let's give Sarah. So now give time to Vinsu and see if there's any questions for Sarah.
Theodoros, do you want to go ahead and ask your question?
Okay.
I think you never mentioned this in your discussion anyway, but you have been talking about creation picture, the creation operator.
Yeah, well, that's where the dual immaculates in NSIM, or sorry, the immaculate functions in NSIM came from these creation operators in NSIM.
Yeah, well, yeah, thanks. But what I was trying to say is there a reverse process like annihilation picture?
Could be. I haven't looked at that. That would be something. I guess that, yeah, the first person to ask about that would be the if any of those Berg, Bergeron, any of them are here, because that was where the immaculates came from, this creation. But yeah, that would be something interesting if it's not already known.
And I saw something in your slide. So can we go to page 8?
Sure. I don't know if I'm still shared, but
If not, that's okay.
Yeah, so the combinatorial, the tableau.
Maybe if I recall correctly, you had an expansion in terms of yang, right? A positive expansion. If you drop yang, would it be positive expansion?
Are you talking about the dual immaculates into young quasi-symmetric Schurs? If you drop the young, it's not positive, and that's why we have to go to the, that's where the reverse family comes in. You kind of need to toggle between these two different families.
Oh, got it, thank you.
Other questions, comments? I see that Mike has a comment. Oh, Sammy, do you want to go ahead?
Yeah, Sarah, that was a great talk. If it gets distracting, sorry, I've got people pounding on my roof right now. So sorry if you can't hear this, but I was just wondering, you have these young key polynomials. Do they expand into the young slide polynomials the same way that keys expand to the slides?
Yeah, they should, because as soon as you have like the full reverse picture, and the full, like all the polynomials that you need, you can translate any formulas. Like,
so have you guys tried reversing a Schubert polynomial to see if anything interesting happens when you try to relate Schuberts to like immaculates or something like that? Because you could just directly define a reverse Schubert using your machinery here, and then expand it into immaculates.
Yeah, that's what we're working on right now. So
okay. Let me know what comes up. That sounds.
I will, absolutely.
Okay.
Wouldn't reverse Schubert just be Schubert for the corresponding Schützenberg, like the W naught, pi W naught?
I don't think so, but it doesn't seem obvious to me. Maybe Sarah Billy would know the answer to that, but that doesn't seem obvious.
It's modulo the coinvariant ideal. So Dari's claim is modulo the coinvariant ideal, I believe.
I wasn't meaning it that way, but okay, maybe. Okay, well,
Sarah's answered.
I believe Sarah knows.
Yeah. Other questions? Hands up, nobody. In which case, it's back to Anna.
All right, so thanks again for both of our speakers. Really great talks today.